So welcome everyone. Thanks for joining. This is the second part of a three-series meetup. Basically, the three parts do this. The first one did this demo 1 from container set 1. Today we're going to do container set 2, and in 2 weeks we're going to do container set 3. What's interesting about the three differences is what we presented last week was you see these 10 containers, each running Nexus and LISP together using a 11th container called MRMS, which is the LISP mapping system to resolve EIDs to locators. What we're going to do today is show you 10, we call them decent XTRs, meaning decentralized, and they're going to use each other as the mapping system. So the MRMS container won't be involved today. Should be pretty short, but trying to create a segue into next week and then some of the new things we want to report on what we're working on for Tritium, the Tritium release. Okay, so if, let's see. So I have this window here is the 1 XTR, XTR1, and this one on the right is 10. And what I started to do is just started to do a ping. Let me restart that. Okay, so what this is going to do is it runs a script where XTR1 is sending ping messages, IPv4 ping messages to itself and the 9 other containers. And I'll show you why that's important in a second. Oh, how do I, oh no. I can't stretch the top. Let's see. Oh, there we go. Okay, so just to show you what the topology looks like, more continue. Okay, let's see if I can stretch this a little bit. Okay, so what we have set up here is that we have 10 containers, Docker containers. They're running Debian Linux. They're running a Lisp at the network layer and Nexus at the application layer. Okay, this will just give you some idea on so what's interesting is not only is it an XTR, but since we want to run a decentralized mapping system, we want the map server or map resolver component of LISP to also run on each of them. So that's why you see these two different processes running here. If we just go look at any one of them, like for instance XTR1 here, we'll show that it's doing the ITR function, the ETR function, which means it's encapsulating packets and decapsulating packets as a regular data plane Nexus node, but it's also participating in the mapping system. Okay. Now, when you look at the topology, let's look at what this system would do. So this is, if you look up here, this is XTR1. It is configured with an EID of 240.0.1.1. Okay. So that's the source address that Nexus will send packets from to everybody else, all the other containers. What's interesting though from the topology is we have it connected on 2 logical interfaces, Ethernet 1 and Ethernet 0. We're trying to make it multi-homed, so it allows anybody that's sending packets to the system could use either one of these interfaces. So we're using the Docker underlay to basically deliver packets, but it looks like that these connections are double connected, very much like this is what we're showing here. Each XTR has 2, like if they were connected to Ethernet directly, 2 connections. And that's what you see. The 20027 is one of the RLOC addresses that the underlay delivers to, and this is the Docker address, 172.17. So basically any system could load split packets across it. What this green is telling you here is packets are coming in from various places using this particular RLOC right now. This is the decapsulation side, the ETR side. If we go to the ITR side, the encapsulator, it's showing you what the map cache looks like. The map cache basically is telling you that the system is sending to a lot of different EIDs here. And notice they're all mirror images. They're all multi-homed. So you see these two RLOCs are associated with decent XTR2. Here's 3, here's 4. And you see the green means we're actively moving packets. Light green means we've sent packets to it in the last minute. Dark greens means we've sent to a packet in the last second. Okay, so basically everybody's sending packets to everywhere. We can show that if we do this, we can show you the number of TCP connections that are up. So this is XTR10, and it's basically showing that it has a connection to 5, 4, 3, 2, 1, 6, 7, 8, and 9. So those 9 other places. And if we went to XTR1, it has the same number of connections. What the ping script showed is just that we're sending ping messages. But what's more important is that these TCP connections are being set up by the Nexus code. And so that's how they're all talking to each other. So they're all talking to each other. They all could send transactions and Nexus pings and stuff like that. There's all communication from the network layer. But what's most interesting about this deployment and design is that the mapping system itself, so if you look at the map server component in XTR1 here, you'll see that it knows about registration for all the EIDs. And let's say we went into XTR8, that's described by EID 240.0.8.8. What you would see is the EID being registered, of course, and then the 2 RLOCs. And that allows any system that queries this mapping system to, or this map server, to be able to get this RLOC set to send packets to. But what's interesting about the decent design is that when this system needs to send, it doesn't have to go outside and ask anybody for the mappings, because it's its own map server as well. So if you look at here and you see that what's the map resolver, basically says I'm going to send map requests locally to resolve EIDs to localhost, which means myself. And because it's a map server, it can respond back to itself and therefore populate this entire map cache. Okay. Now, if we look at the configuration file for 1 minute, we can see that when you configure this system, it's only registering to one map server. And the map server turns out to be this 239.222 address. That is a multicast address. Okay, so that means when this system is registering its EID to locator mappings, since this is XTR1, it's advertising EID 240.0.1.1 with the RLOCs of each of those interfaces, it's actually sending those updates to a multicast address. So all other XTRs are receiving this at the same time. So if we wanted to go, oops, let's go back here. Where was I? Here. Let's go back to the browser, and oh, I should know this. What happened? Everybody still there?
Yeah, we're still here.
Okay, that's good to know. The problem is this top bar. It basically, I can't move. Okay, there. Now I'm squared away. Okay, so what's happening if we went? So this is just basically saying this port number maps to XTR1. If we just increased it by 1, we talk to XTR2. See XTR2 there? And if we looked at its mapping system, it looks exactly the same. There's XTR3, looks exactly the same. So what's happening is these map register messages, each of the XTRs are sending their mappings to the multicast address. Okay, what happened? Okay, there we go. So you see that what's happening is that these XTRs are actually joining this underlay address, and these messages are moving. In fact, we can actually look at the activity by just doing a TCP dump on 4342, which is the UDP port number that LISP uses. syntax error. We'll just watch a little bit. So you see all the activity that's going back and forth. Let's not show the RLOC probes. Let's do this. Let's just show the map registers. And they're each sending it once every minute. So while we're talking, we can just watch the TCP dump there, just showing you. So what the idea here is, normally when you have a mapping system, I can't find my other window. I'm trying to get back to the slides, and I think I accidentally turned it off. Let's see. Okay, so normally when you have the mapping system, it's kind of part of the infrastructure, just like DNS does. What we want to experiment with in the crypto world is making it decentralized at the same time as the peer-to-peer network is at the Nexus layer. Now, this is a push proposal. That the first internet draft that Colin and I published together in the ITF back in March. The first proposal was to make it use multicast and have it completely distributed, so there was really no configuration. If all the XTRs and Nexus nodes came up knowing that the address was, I don't know why the map registers aren't coming. Maybe it's because, here's some map registers. Maybe my grep wasn't working. Let's just keep going like that. So if everybody just comes up and they know what the 239 address is, or any multicast address, then each multicast address that's being used can denote a mapping system, and that these things could come up plug and play. Now, in a wide area network where you may not have multicast everywhere, these systems could head and replicate, provided the multicast addresses are in the mapping system. Now, another way we want to do it, this is called a push approach, where everybody's pushing out the mappings to all the map servers. We want to implement a pull approach where we can basically hash the EID into a number between 0 and n, and then we have map servers that are deployed at certain DNS addresses. So for instance, we'd have map server 00 through map server n-1. Those would be names that would be in the DNS. And these systems would look them up, get the addresses from them, and then just send unicast map registers to a specific one. So for this particular EID, the modulus might be 0, it might be 6 here, it doesn't matter. But since all the map registers and map requests are using the same algorithm, the same modular math, you can then have this thing distributed and have some either seed nodes or peer-to-peer nodes be part of the mapping system. How you deploy this is something that we plan on experimenting with over the next several months. The first mapping system that we're building is a traditional LISP mapping system that's going to be part of the seed node configuration as Nexus is deployed today. And we'll be able to talk about that in a future meetup. But this is just showing you some of the more advanced or research topics we're working on with the mapping system. So let's see, did I find any map registers here? There should be more map, I don't know why they're not. They are certainly working. Here are some, let's see, let's look at these. Okay, yeah. So what's happening here at this time was 36 was sending, so 1, 2, 3, 4, 5, 6, 7. Those are 7 systems. There should be 9. Let's see, is there any more? They're probably sending them at different intervals. Looks like the clocks are synced and these guys are sending them in the same burst. But we see all the registrations, so I just can't find, here's one right here that came up. So it looks like 2 of the systems are a little bit time skewed where they're sending map registers differently. Let me do this. Map. We'll go in reverse direction. So let me come to the end and then go up. So that's 33. And then here's the sequence of 7. There's 28. there's 35, there's 33, and then a sequence again. There's 28, there's 35. So those three are out of sync, which is a good thing because you want to distribute the load. If you use jitter timers in your implementation, these things don't get synced up, so it works pretty well. Turns out all the systems were brought up at the same time with a script, so that's why some of them are synced up. So that's basically the, let's see, let me do this. Go back. So that's basically the demo. We're showing n-squared connectivity among these decentralized XTRs. Nexus connections are up, moving messages. So what we want to do next time in 2 weeks is we're going to bring up a lot more containers, and we call them crypto because they're going to be using IPv6 EIDs, and we're going to show how IPv6 could run among the Nexus nodes over an IPv4 only overlay, both multicast and unicast. And in this case, we're going to show that the MRMS is actually centralized as well. But you can take the robustness of the Lisp architecture allows you to mix and match all these variants. What we wanted to show at the conference was that we had all these various ways of doing networking. And now we see what the capability is, we've tested it, we're able to package the Nexus and Lisp code together, and now we're actually starting to deploy stuff in anticipation for Tritium. So let me pause for comments and questions. Looks like we're up to 13, that's great, people. And let's see, I'm trying to bring why do I always not find the chat window more? Do you know where the chat window is, Anastasia?
It's at the bottom of the Zoom call.
Oh, it's because I'm in the share mode. That's why I don't
Yeah. If you unshare your screen, you should be able to see the bar at the bottom.
Got it. Okay, wonderful. Okay, so that was kind of quick. I guess we're on schedule, I guess. Any questions, reactions, comments, questions? Any question is valid.
You guys can unmute yourselves if you have one. Or you can post them in the chat and I'll read them.
Hi, Dino, can you hear me?
Yes, I can.
Hi, this is Andrew Hatzstead. I'm in Pennsylvania. First, thanks for giving this series of updates. It's really quite informative. I'm trying to come up to speed with what you're doing. I was wondering if for some of us that aren't quite down at the detail level where you are, can you take us up a level or two and talk about what's the big picture? What's the killer app that people can use this Nexus Lisp infrastructure to accomplish?
Sure. So at the high level, what we want Nexus nodes to do, either wallets or miners or even daemons, is we want them to have multiple connections to the network without having Nexus maintain so many different TCP connections. So by Nexus just supporting a connection to the EID, if your particular miner has 4 physical connections in a data center, you could multi-home and use all those connections. What Lisp is going to help Nexus is that we're going to have underlay telemetry information telling them which one of those underlay physical connections could be used, and we're going to be able to give much better performance to the application. So that's just one benefit. The other benefit is since the Nexus node will have an EID assigned to it, the EIDs can actually move around, and those physical or wireless connections, the RLOCs that are part of the underlay where you attach the network, can change dynamically, and TCP connections can stay up. So when you go from one node to the other, say you're running a wallet on your laptop and you move from your house to your work to a coffee shop or whatever, those underlying connections will change, and therefore the IP addresses, the routing locators change. But the EID that's being used by the Nexus application does not change, and therefore you have this mobility and could actually keep TCP connections up. That means you'll sync faster, you'll get better performance, those sorts of things. LISP also will provide encryption when it encapsulates packets from one EID to another. So all your transactions will remain private. We don't have that right now in any of the cryptos. They'd have to build it into the application, which they can do. But if you have something underneath, in fact, if you run LISP and use EIDs for all the applications on your laptop, you're going to get that benefit as well as for Nexus as well. What we're also going to do is have anti-spoofing. So today, it's easy for a wallet or any Nexus node to spoof their IP address. With these crypto EIDs, you're not going to be able to do that because the crypto EID is based on your key pair. And we're going to use the key pair at the Nexus layer and at the LISP layer. And the crypto EID will be part of your Genesis block and part of your SIG chain. So therefore, there'll be a tight binding between the two layers. So this is just going to bring a new level of security to the system that we haven't seen before. By using multicast underneath, we can allow nodes in different pockets or pools to communicate with each other. We can do admission control if we choose to through these groups. And then Nexus only has to send out, if there's 100 nodes that are joining the same multicast group, a Nexus node only has to send one packet. Today it has to send 100 packets over 100 TCP connections, right? So these are additional performance improvements that can help. Anastasia or any other Nexus folks on the call want to add to that, please do.
I think you pretty much covered it. Yeah, the high level is really that the connections are going to be faster and more efficient, which, because it's on the network level, gives our entire network that effect of being faster and smarter and more efficient.
Is that high level enough for the person who asked the question? Or not enough?
So I think I understand what you're trying to do. What I'm trying to figure out is if I'm just some average person who's trying to write a network application, what's the ideal network app? Let's talk in terms of things that are a little simpler, like a chat application or I don't know, some kind of banking application, or what is it that you're gonna sell me on that I'm gonna say, wow, this is great. I want to design my application on this infrastructure as opposed to just a regular TCP connection or something.
Right. So the contracts platform in Nexus is going to be very useful. We've decided to take some different approaches than which already exists. We don't want the contracts platform to be a programming language where software engineers are the only ones that can define contracts. So we're going to have a really simple way of building contracts where you can change ownership, you can change royalty rights, things like that. You can do voting systems, you can certainly do chat groups. But what we're trying to do is we want you to create these data structures or storage registers, as we call them, object registers, and they allow you to transfer ownership of anything, supply chain, titles for housing and real estate. And by doing this, you're able to put things on the blockchain, not only just to move the coin and to mine the coin, but to provide all these other use cases. And in time, we're going to release and let you know the use cases that are running on this infrastructure as they get deployed. Does that help?
Yeah, it does. Thank you.
Cool. So Chris Murdoch has a question. He also thanks you for the updates, Dino. And he says, does LISP need to be on certain hardware like routers to make it work? Or is it all code based on top of the hardware layers?
Yeah, really good question. So the way we design the architecture is we believe that the underlay is the existing capital I internet. So all the routers and switches, firewalls, load balancers, all that infrastructure and system that runs on the internet today continues to run, and we don't require anything specific for them to work. That's the beauty of an overlay. So we're going to use IPv4 unicast because that's what's ubiquitous across the internet, across the globe. We're going to just use that infrastructure. And what we're going to do on the overlay is do these new types of things like run multicast, run IPv6, and those sorts of things. So by putting this network type functionality in the end host, in other words, right next to where Nexus is running, we can do this all over the top. So it requires no intermediate boxes. It also allows you to NAT traverse wherever you're running NAT. And NAT is pretty much ubiquitous. If you're on a cellular network, you're going through a NAT. If you're in a cloud provider, you're going through NAT. If you're sitting at home or a coffee shop, you go through NAT. So we want all these systems to connect to each other regardless where they're located.
Cool. He says thanks. That was clarifying. I don't see any other questions in the chat, so if anyone else still wants to jump in, please go ahead. Looks like we're all set, Dino.
Yeah, if anybody has any other questions, we're available on the Slack and Telegram channel. So, if you think of something later, don't hesitate to ask. We'd be glad to answer and start a discussion.
Cool. Thank you, everyone. Thank you, Dino.
Thanks, guys. Appreciate it. See you next time.